Okay, so this discussion that I've just given you of anti-screening, this first appeared in a paper of Appelquist, Dine, Musinidi in Physics Letters 69B in 1977 and on page 231. You might like to take a look at this paper to read it. It describes what we've just discussed about anti-screening. I will be sending you this paper so that you can take a look and read it, and it'll give you a chance to see what it's like to read the original literature. So I would strongly encourage you to take a look at that. Okay. So how are we going to use this for the Banks-Zaks fixed point? Well, typically inside your theory, you would have some parameters that you can choose. So one of the things that you would choose is you would choose the number of flavors. So this is how many different flavors of matter you have in your theory. And by choosing NF, you're determining how much screening happens because it's the matter that screens. The second parameter that you can have is your gauge group. So we took SU2, but you could have taken SUN, with n being any integer. So this is your gauge group. So this determines your gauge symmetry. And how many gluons would you have? You would have n squared minus 1 photons or gauge bosons. And these would all be anti-screening. So this will set for you how much anti-screening you have. So you've got two parameters that determine the screening and the anti-screening, and then you would go away and calculate your beta function. Okay, so this I'm going to do very schematically. We're not going to do this in detail. You know what's going on. Well, the beta function would be equal to, this would depend on the theory that you're looking at, the precise powers, but there is, for example, a theory where the first term, the beta function, comes with a g cubed and it's negative, and the second term in the beta function comes with a g to the 5 and it's positive. And these difference in signs, the minus and the plus on the two sides of the beta function, this is precisely what we've been arguing for, the screening and the anti-screening. There are two effects that can be balanced. And you would set this equal to 0, and you would then again solve for the coupling. So once again, there would be a critical coupling. So you'd again have to tune things to get to this critical point. And in this case, I think the critical coupling would be A over B. And if you are smart in your choice of the number of flavors and the number of colors, you would be able to choose things so that this is very much less than 1. And with that choice, you would be able to study the CFT in perturbation theory, and you could use Feynman diagrams and all of the usual techniques from perturbation theory. Okay, very good. So that's our second example of a CFT, also perturbative. You've now got the Banks-Zaks CFT and the Wilson-Fisher CFT. So you've got some idea on how we can construct some conformal field theories. Great. Okay, now we're getting near the end of this introductory chapter, but the last thing I would like to ask is a natural question that maybe even you've asked yourself already. So we've motivated studying conformal field theory because we said theories with symmetry are simple. So symmetry, let's just say it implies simplicity. Okay. So because you know that theories with more symmetry are simpler, the thing you could ask yourself is, what is the maximum amount, so most symmetry, a theory can have? And it's nice to determine what's the most symmetry a theory can have, because the theory with most symmetry should be the simplest theory that we can think about. Well, this answer has been studied a lot since the 60s, and I think that we've got some pretty good answers. So I want to explain to you the answers that we've got uh, to this question. So the first really important result, this is maybe the most important of all of them that we should discuss, is called the Coleman-Mandula theorem. And the idea behind the Coleman-Mandula theorem is the following. So I'm not going to prove this, but I'm going to try to explain it to you so that you know the logic behind the proof, even if you can't do all of the details. So Coleman and Mandula think about scattering of two particles. So we've got two particles coming in. They scatter, they interact somehow, and then these two particles go out. And I could give these two particles momenta, P1 and P2, and P3 and P4. And then we start to think about how much symmetry can we impose on this S matrix. So the way that we would describe the scattering is through an S matrix. And there's a few things that we know, something physical that you must have. So let me put this down here. So you must have that the S matrix is an analytic function of two scattering angles. So this is analytic function of two scattering angles. Now, where does this constraint come from? Actually, the S matrix has to be an analytic function of these scattering angles so that it has properties like unitarity and causality. So this is needed for a physically sensible theory. There's a lot of theory behind this. I'm not going to explain that. I'm going to ask you to just accept it on face value that the S matrix must be analytic. This is related to deep properties of the theory like unitarity and causality. So it's needed for a sensible theory. Good. So what does the S matrix depend on? So S will depend on P, these momenta. So let's call it Pi mu. And I can go over 1, 2, 3, and 4. Mu can go over 0, 1, 2, 3. So this is a total of 16 parameters. Okay? And then the logic that we're going to use is that every time we have symmetry, okay? Every time we have symmetry, this means that there's a conservation law. And every time there's a conservation law, it means that there is a constraint. So you see, symmetry eliminates parameters because symmetry enforces constraints. And so by putting a whole lot of symmetry on, you start to reduce the number of parameters. So let's now start to look at the constraints that you have. So one constraint that we have not related to symmetry is just the following. We know that Einstein told us that E squared minus P dot P is equal to M squared. You will have used this in your first quantum field theory course a lot. We certainly used it a lot last year. And this can be written as P mu, and that will be written as P squared. Now this mass shell condition must be satisfied by each of our momenta. So we'll have P1 squared is equal to M squared, P2 squared is equal to M squared, and P3 squared is M squared, P4 squared is M squared. This is 4 equations. So after we've imposed these equations from our 16 parameters, we have 12 parameters that remain. And then after those 12 parameters now, let's see what we can have for actual symmetries. And let me tell you what Coleman and Mandula say. Coleman and Mandula, they say maximum number of symmetries is equal to Poincare invariance. And I should be a little bit careful here. Okay, so we haven't discussed this in detail. Maybe we will, haven't decided yet. But there are things called space-time symmetries that would act in a non-trivial way, for example, on momenta of particles. And Poincare, Coleman-Mendula theorem is really a statement about space-time symmetries. You can have things like gauge symmetries, flavor symmetries. Those are not fixed by Coleman-Mendula theorem. Those would be called internal symmetries. An internal symmetry would not act on your momenta. So here we're fixing a space-time symmetries. When we say we've got Poincare invariance, what does Poincare invariance correspond to? Poincare invariance means you've got translations. So there are 4 translations in time in the 3 spatial directions. That's a symmetry of the theory. And then you've also got Lorentz. So you've got rotations and boosts. So there's a total of 4 translations and there's 6 Lorentz transformations. And the logic is, for example, look at the translations. From the translations, we have some symmetries. What they tell us is energy and momentum is conserved. So P1 mu plus P2 mu, the sum of the 4 momenta before the scattering, has to be equal to P3 mu plus P4 mu, which is the sum of the momenta after the scattering. This imposes another 4 conditions. So this is 4 conditions. And so what you get after you finish this, you get a total of 8 parameters. Now, in exactly the same way, if you do careful arguing, which I'm not going to do, from the Lorentz, you get another 6 conditions. And from those 6 conditions, you finally land up with 2 parameters. So the S matrix depends freely on 2 parameters, but actually that's as small as you can go because we know that the S matrix must depend on theta and phi. So you cannot have more space-time symmetries than you have from your Coleman, from Poincare invariance. So the Coleman-Mendula theorem, the main thing, okay, so what are the key ideas that I want you to take away? We didn't prove the theorem carefully, but here are the key ideas. So you have a theory. For it to be non-trivial, it must depend freely on some number of parameters. For it to be unitary and causal, we know that it must depend on at least 2 parameters. It must depend on at least 2 parameters to become causal and local. Every time you have a conservation law, that implies another constraint, so it eliminates a parameter from your theory. Once you've got translational symmetries and you've got Lorentz symmetries, in fact, you've eliminated so many parameters that you're just left with those 2 parameters, so you can't eliminate any more. So the maximum number of symmetries that you can have is Poincare invariance. Now, once again, I haven't talked about these internal symmetries. So we've been thinking about fixing things like your momenta, your space-time momenta. Remember in the case of the non-abelian Yang-Mills theory that we just discussed, well, there we said we could have flavor symmetries that match different flavors of the matter. So the matter could come in different flavors, like quarks. You can get up quarks, down quarks, whatever. So that up, down, bottom, those are also additional parameters that are not like momenta. The flavor symmetries would act on those labels, bottom, top, down. So we haven't talked about those internal symmetries that act on labels like the flavor labels. They could also act on the color of the photons. But as long as we're just looking at space-time symmetries, the things that do act on the momenta, there's a biggest possible set of symmetries that you could have, and that's given to you by Poincare invariance. So I just want you to be aware of that result. What I would suggest, we've gone through this very quickly. There's so many things that you could have said in addition. So I would suggest you look this up. on Wikipedia or something like that and just read through what the Coleman-Douglas theorem says, or take a look at a textbook, read through what the Coleman-Douglas theorem says. I would just like you to be familiar with this idea that there is actually a maximum amount of symmetries that you can have in a theory, and that's given by the Poincare group. Okay, we'll continue in a moment.